Good afternoon, everybody. We'll get started here in about 5 minutes or so. Thanks for your patience this afternoon. We'll give it about a minute or two and then we'll get started. Thanks for your patience. All right, I'm going to go ahead and get started in the interest of time. We'll try to make this a fairly short meeting. So, first order of business, I did forget to post the video from last Wednesday. It will be posted here shortly. I submitted it to YouTube for captioning. So as soon as it's available, I will post the link to it in the announcements. I do apologize. I got caught up in a holiday break as well. So uh, I'll get it out there for you here shortly. So I'm going to go ahead and share my screen. So you should be seeing the course homepage. Somebody confirm that for me. Just unmute and say, yeah, I can see that.
Yes.
Thank you so much. I appreciate it. Um, so in the announcements, I posted for you. It's taking a moment, but hopefully it'll come up here shortly. I apologize. There we go. I posted the project video that discusses the summary that you have to write and how I'm going to score that summary. And what I want to do is answer any questions you have about the video. Now, here's what I'll do. Um, of course, I can always take your questions via email or however you choose to communicate with me. But let's save this for Wednesday. That way you have time to go and watch the video. That is your assignment between now and Wednesday. I'm not talking about anything that's due Saturday. Between now and Wednesday, you need to go into the announcements and watch the project video. When we get back together on Wednesday, that's going to be the order of business. Okay? Covering and answer the project video, answering any questions you have about the project, the summary, or the scoring. All right. So just in case you hadn't seen this video, it has been out there for a few. I'm delayed in putting the video from the 30th out in the announcements, but the project video has been there for a little bit. So that'll be Wednesday's discussion. We'll talk about the project. You come prepared with your questions. I'll come prepared with some answers. So now what I'm going to do is go into the weekly overviews for this week. All right. So here we are this week. Now, the astronomy video, the astronomy overview is something that you cover on your own. You will go into the astronomy overview. Sorry, again, I've been having a lot of internet troubles lately. I'm glad I could be here today because earlier my internet went out on me. So, um, so for the astronomy overview, you will review the notes and the videos on your own. You will complete the discussion. Problem set 12 actually deals with waves, which I'm going to actually talk about here shortly. But the astronomy overview is something that you deal with on your own. I don't actually cover it, okay? You can ask any questions you have about it anytime you need to, but there are notes and videos here, and I don't really go into it because it's the kind of material that you can read and digest on your own. There isn't any problems that you solve or anything like that. So, you know, you can go into it and read through the material yourself. It's a really interesting topic because they talk about things like black holes, dark energy, dark matter. So take a look at the information that I have out there for you. Again, any questions you have, I'll be happy to answer, but this is an overview that you're going to work through independently. Okay. Now, the overview on waves, I'm going to take a look at that material today. Okay. I'll go into that. Again, I do apologize. This is a little bit frustrating, to be honest, that it's taking so long. All right, there we go. So now let's get into waves. Okay, so you can see from the objectives that are listed here, we're going to be looking at waves, and waves is kind of a big broad overview. We'll drill down into some properties of waves. We'll look at the interactions of waves with matter, and so that you know how to calculate certain properties regarding waves, in particular problems that deal with the speed of sound. So we'll take a look at all of those, okay? All right, so for waves, you do have a discussion, just like always. Problem set 11 that's due on Saturday, and just a reminder, that actually deals with thermodynamics that we covered last week, okay? So, problem sets kind of lag behind because those are homeworks, all right? So here's the reading material regarding waves. So you can see that chapter 11 in the textbook deals with waves. Remember, the textbook is a resource that you are supposed to be interacting with to cover the topic, and the videos that I put out there. I did include an optional set of information on gravity waves if that kind of interests you. I always, it's not something that I include as like material you do homework on or get tested on, but I put it out there because it's a very relevant topic to Louisiana, because a group out of LSU and LIGO, which is actually in Livingston Parish, the interferometer that they run out there, the team that runs that interferometer and a group out of LSU actually won the Nobel Prize several years back for their study of gravity waves. So I thought it's cool that we're talking about waves. We've talked about gravity. Now we can see how those two topics mesh together in this very relevant and new topic that's being investigated. Maybe some of you have an interest in gravity waves and you have chosen something related to that for your project. I don't recall everybody's project topic, but maybe that was something you're interested in. Well, now you have some material that discusses that in our lecture, readings and viewings. All right. So let me go into this notes on waves. Hopefully this will open up here. Yeah. Okay. Oh, let me see if I can download it. Oh, there we go. So while this is opening up, I just want to ask a question. Anybody who knows the answer can unmute and answer it for me. So if you are a P-Tech student, and I don't know any of your backgrounds, do you all take a fluid mechanics class? I'm just curious. Do any of you know?
Yes, ma'am. I took one already.
You took it already, Mr. Tyler Capps. You took that course
Yes, ma'am.
already?
Yes, ma'am. I took it 2 semesters ago.
Oh, okay. So I apologize. This must be like really boring because a lot of the stuff that we talk about here, you kind of need that as a background to do fluids. Am I right in saying that?
Yes, ma'am.
Yeah. So at River Parishes, they make students take the physical science and algebra first and then take fluids. The reason I'm asking is because I would love to be able to teach a fluids class at Nunez. And so I didn't even know if you offered that course. That's why I'm asking.
Yes, ma'am. I think they got it's like one guy and then maybe another guy that teaches like 1 or 2 classes, but they have one main guy doing it.
Okay, got you covered. Okay. Thanks a lot for clarifying that for me, Tyler. All right.
Matthew had took an automotive class before, but it's not really related to it.
Okay.
Delgado.
Gotcha. Okay. Thank you very much for that. All right. So what we're going to be looking at in this packet here is oscillations and waves. Okay. So I want you to kind of think back now. I mean, I know this class has gone by so quickly because actually, when you think about it, this is the last topic that I'm going to lecture on because you'll do astronomy and the applications overview on your own. So this is the last time you have to put up with me doing a lecture. Okay. So if you think back, to several short weeks ago, and reflect on all the different types of motion that we've covered so far. So we've covered horizontal motion, we've covered free fall motion, we've covered projectile motion, we've covered circular motion. We looked at how forces are relevant to motion. We've looked at energy, we've looked at momentum, because momentum allows us to analyze collision type motion. But what we haven't analyzed so far is back and forth type motion. What things are relevant if an object is moving back and forth or oscillating, like a child swing they give as an example. You push the child swing, it goes back and forth, right? A pendulum clock, that's another example of oscillatory behavior, or the pendulum bob on a pendulum clock oscillates back and forth. And also, if you ever get to the point where you're dealing with microscopic particles, atoms, and molecules, you'll find that they also oscillate. Even solids, even things that we typically think of as solids, have atoms and molecules that are oscillating, moving back and forth. They just have a kind of a restricted space where they can oscillate. Those atoms can't oscillate out of a restricted area, or then the solid material shatters, right? Or, a liquid, for example, has atoms and molecules that are a bit more free flowing compared to those in a solid, for example, but those molecules also oscillate. And so when an object is moving back and forth, the oscillation might create a wave, okay? And that wave is a disturbance that moves out or propagates from where it was created. So whatever is oscillating can create this wave which moves out from the oscillator. Don't confuse the object that's oscillating with the wave that it creates while it's oscillating, okay? It's very important to have the distinction very clear in your mind. So, for example, if you pluck a guitar string, that string oscillates back and forth and creates a sound wave. And that sound wave, disturbs the air. And another example is an earthquake. That earthquake consists of a wave, a seismic wave is what we call an earthquake. And that wave travels through the ground. And then, we could have things that oscillate that don't have mass. I know that seems kind of weird, because we deal so much with objects that have mass and take up space, matter. But there are things that oscillate that don't have mass. And that's light, for example, and other forms of electromagnetic energy, things like radio waves, microwaves, gamma rays, X-rays. Those are all forms of light. They're just not visible, but they also oscillate and create this wave that travels, in this case, through empty space. So that sound wave that comes off of that guitar string has to have air. It has to have a medium to move through, but these electromagnetic or light waves don't have to have a medium. They can travel through empty space. And you might ask yourself, for this electromagnetic wave, this light wave, what is it that's oscillating if there's no mass involved? Well, the electric and magnetic fields are oscillating perpendicular to each other to form a light wave, okay? So these things that oscillate, these oscillators, whoa. I'm sorry, I lost you guys for a moment. I told you that I've been having a really difficult time with internet service lately. I've had Cox out here a couple of times. So I do apologize. Sometimes you just have to accept there are some things beyond your control, but I'll do my best to get through this. So I'm going to share again. All right, so here we are where.
Can you also repeat the last example that you said before you switched slides?
Yes, I will be more than happy to do that. Bear with me just for a second. All right, so I was here. I was on this slide and I was talking about electromagnetic waves, okay? And so various forms of light, like microwaves, radio waves, gamma rays, UV, ultraviolet radiation, infrared radiation, all of those are actually light, but only a small portion of the electromagnetic spectrum is visible light, okay? And so that light consists of energy that causes a wave that can travel through empty space, okay? And so even this light energy that doesn't have mass can oscillate. And in the instance of light waves, it is the electric and magnetic fields that are oscillating perpendicular to each other, creating this wave that can travel through empty space. Okay. Now the sound wave that disturbs air, it has to have a medium. It has to have the air. You know that saying, if a tree falls in the forest and nobody's there to hear, it doesn't make a sound. Well, if there's no air, all bets are off. Nobody's going to hear anything, because sound waves have to have a medium to propagate. Okay. And most times that's air. Okay. But light, electromagnetic energy, can travel through empty space. And actually, for any wave that's being created, it is the energy that is propagating. It is the energy that
I
is.
have a question.
Yes.
So you must have air for sound, but I found an article that was on Facebook that was talking about the sun and how that creates noise, but we can't hear it because it's blocked.
Well,
So is that,
let me clarify that. Let me clarify that. When I say sound has to have air, actually sound needs a medium of some sort. There are sounds being produced all over the world right now that you're not hearing. There's a jet plane taking off in a country away from here. You can't hear that sound, right? But it is being created, right? So it is very much possible that the sun is making noises of some sort, and we can't hear it in our space. Maybe there's some type of detector that is detecting those sounds from outer space. But what I'm saying is that unlike light, which doesn't need a medium to travel, sound needs some type of medium. And most times for us, it's air. I'm not saying all the time, because sound waves can travel in through solids. In fact, sound waves travels best in solids, then liquids, then gases. It's why if you want to spy on someone, you put the spy glass, which is a solid, to the wall. Okay. So hopefully that clears up that slide before I got disconnected. So let's hope I stay connected to get through this one here. So those objects that oscillate, we want to focus on the simplest type. We're not at all trying to deal with this in a complicated fashion. So we're going to focus on those simplest type of oscillations and waves. Those type of systems that exhibit simple oscillations and create these simple type waves are described by Hooke's law. Remember now, law is focused on a very restricted type of pattern that we observe and measure in nature, right? And so simple oscillators can be analyzed and described using Hooke's law. And Hooke was a scientist, and he was one that was very instrumental in helping us to understand oscillations and waves. And that's why it's named after him. And so remember, a law, because it's relegated to a restricted type of pattern that we observe in nature, can often be represented using a mathematical formula. And here is the formula that represents Hooke's law. F equals minus kx. Okay. So in this formula, F is what we call a restoring force. And I'll explain that in just a moment. X is the displacement from equilibrium that our oscillator experiences. And I'll kind of give you an example to help you visualize what I'm saying here. And so sometimes we say that X is the displacement or the movement away from an equilibrium position. Sometimes, depending upon what type of oscillator we're describing, sometimes we call that the deformation, meaning how much is our oscillator deformed from its equilibrium state, okay? In this equation, the letter K is a constant, okay? And we call it the force constant. Sometimes you will hear it referred to as the spring constant, okay? Because springs obey Hooke's law, okay? So they give you the unit for K, and that's newtons per meter, because K tells us how rigid or stiff our system is, our oscillator is, and we measure that stiffness in newtons per meter. How many newtons of force do you have to apply to stretch our oscillator a certain distance from its equilibrium? And we know we measure distance or displacement in meters, okay? So for this spring constant, so you know how it behaves, the larger that constant is, the greater restoring force we need to return the system to equilibrium. The bigger that K is, the stiffer our system is. So let me give you an example here to help you understand. As I mentioned, K in this formula is a lot of time known as the spring constant, okay? And so let's look at two different types of springs to kind of get our mind, wrap our mind around this formula, okay? So one spring that I'm gonna talk about is a slinky. Everybody knows what a slinky is, right? Slinky, a slinky, the magical, wonderful toy. Slinky, a slinky, great for a girl and a boy. I mean, that was the commercial that was out when I was a kid, right? To entice people to buy slinkies. Well, a slinky is nothing more than a spring that is very, very loose, extremely loose, okay? And so it has a small spring constant, K, because it's very easy to stretch it. You don't have to apply a lot of force to stretch a slinky, right? Okay. And the other type of spring that I want to talk about is a shock absorber. Now, I may be talking to folk who don't have a lot of experience where cars are concerned, but a shock absorber is what allows your car to move without a whole lot of bouncing, for example, when you hit a bump. You know if your shocks are going bad because you hit a bump and the car just, vibrates or oscillates up and down a whole lot. Okay, and I'm not talking about those cars where you hit the switches and they jump up and down and bounce all over. They have shocks too, but that's not the type of system that I'm talking about here. So a regular shock absorber, if you peel back all the covering and look at it, is an extremely thick spring. And it's extremely thick because it's meant to absorb the shock that the car experiences when it hits a bump, meaning you got to have a lot of force to compress that shock absorber. So it absorbs, motion within the car system. That spring is extremely thick and extremely rigid, and it has a tremendously large K, because you would have to apply a lot of force to be able to stretch it, okay? So it's very good at absorbing the shock that automobiles experience while they're riding and hitting bumps and things like that, okay? Now, there's one thing about this formula that maybe didn't catch your eye right away that I want to explain to you. So we know that F is the force, K is the spring constant, and X is how much we stretch our spring or our system away from equilibrium. But what is that minus sign doing in the formula, right? You're like, It's a minus sign there to tell us that this force is a restoring force. Meaning, whichever way you stretch the system, it restores in the opposite direction toward equilibrium. Okay, so imagine our slinky, and imagine we take it and we stretch it out in one direction. When we let it go, it will restore back to its equilibrium or original position. All right, so that minus sign in there is not about greater than or less than. Like, we typically think of negative integers and positive integers, right? That minus sign is more about direction, because whichever direction you stretch or deform the system in, the restoring force is going to move it in the opposite direction back toward equilibrium. So that's what that minus sign is about. Helps us to know that Hooke's law is a restoring type force. All right. Another important property of our oscillators that we rely on or analyze is the period and the frequency. Those are actually two properties that we focus on for our oscillators, the period and the frequency. Now, period is not a concept that should be foreign to you, because when we study circular motion, if you remember, objects moving in a circle have a period. The period for an object moving in a circle is the time it takes to make one complete trip around the circle. Well, here, when we deal with the period, T, capital T, just like for the circular motion, the period in this case is the time it takes to complete one oscillation. So the time it takes to oscillate and come back to its starting position, that's what we call the period, okay? The time it takes to repeat itself, that's the period, all right? And so this idea of period is important because oscillators exhibit what we call periodic motion, just like objects moving in a circle exhibit periodic motion, okay? So this periodic motion refers to motion that repeats itself in regular time intervals. And an object on a spring, a mass attached to a spring, does that kind of motion where it repeats itself periodically. So it has a period. The other important property is the frequency for periodic motion. And the period is the number of cycles per unit time. So how many times does it repeat itself per unit time? Oscillations or cycles per second, for example, okay? So in the metric system, we use Hertz, and Hertz refers to cycles per second. So how many times does the object repeat itself per second? That's Hertz, okay? And the period and the frequency are inverse of each other. So if we know the period, we can get the frequency. And if we know the frequency, we can get the period, because they're inverse of each other. Don't forget, that also means that their units are inverse, because Hertz is measured in cycles per second and period is measured in seconds per cycle. So they're inverse of each other, okay? So those simple oscillators that we want to deal with, like an object attached to a spring or a pendulum or an object moving in a circle, those are all what we call simple harmonic oscillators. And that is because they exhibit simple harmonic motion, and they can be analyzed using Hooke's law. All right. Now, when we're dealing with a simple harmonic oscillator, there are some properties besides frequency and period that are important. One of them is the amplitude, and the amplitude refers to the maximum displacement. What is the maximum stretch or maximum displacement away from equilibrium in a system? That is called the amplitude. When we talk about waves, we'll see that the amplitude refers to the height, the peak height of the wave, okay? And so we're not gonna get too deep off in the math regarding simple harmonic motion, Hooke's law, and then what we focus on for these oscillators is how do we find the period? Remember, the period tells us the time it takes for it to repeat. And so for a simple harmonic oscillator, like a mass attached to a spring, has a period 2 pi square root m over k. 2 pi square root m over k. That's how we find a period, where m is the mass of our oscillator. So whatever is attached to the spring, and k is the spring constant. Okay, you know, in Hooke's law, they call it the force constant. Well, when we were referring to a spring, we call it k the spring constant. Either one, you can refer to it either way, because they all, this period is related to an object being described by Hooke's law. Okay, just sometimes different terminology that you'll come across. All right, so here's a visual of our object that's attached to a spring. You see on the far left, that spring, the object is attached to a spring, it's not being stretched at all. And then when you let it go, it establishes a new equilibrium position, the middle one, the middle picture. So you let go, the spring stretches, you establish a new equilibrium position, okay? And then think about if we grab the object that's attached to the spring in the middle picture and we disturb it. We disturb it by stretching it a distance x or displacement x or an amplitude x, and the oscillator will begin to move back and forth between negative x and positive x. You see? So it'll go back and forth, right? That oscillatory motion, all right? Another example of a simple harmonic oscillator is what we call a simple pendulum. There are different types of pendulum, and some of them have very complicated motion, but we're going to focus just on a simple pendulum. And we aren't interested in solving or knowing anything else about this simple pendulum other than the period. Remember, the simple pendulum obeys Hooke's law, but to write that force equation for a simple pendulum is a little bit involved. If you look at the picture, you can see things like angles, theta, sine theta. That's all trig stuff, and we don't need to go there, right? But what we want to know is the period, and that is 2 pi square root L over G. Wait a minute. For our simple harmonic oscillator for a spring, it was 2 pi square root M over K. Here is 2 pi square root L over G. So you can see the period follows a similar form in either of these oscillators, whether it's an object attached to a spring or a pendulum. The period has a similar looking formula. Okay, all right. But notice for our pendulum, the mass is nowhere involved in the equation. Notice for an object attached to a spring, the mass matters. The mass affects the period. But for our simple pendulum, the mass does not affect the period. The length affects the period. And notice also that the period depends on gravity. Okay, so our spring doesn't have any dependence on gravity, but our pendulum does. Okay, as I mentioned, an object that's moving in a circle, it is very much connected or similar or correlated or connected to this idea of uniform circular motion and simple harmonic motion. Okay, so those two are very much related. That is because they're both periodic. Okay, and so as our object moves in a circle, it will trace out a wave that is periodic. Okay. There are other types of oscillators. We're not going to go into the various cases of damping motion. When we look at simple harmonic oscillators like a pendulum or an object attached to a spring, we treat it like there's no friction. When we introduce friction into the system, it causes damping. That's all that's about all I want to say about that. Okay. Resonance is an important phenomena. Resonance is what we call forced oscillation. So one object is oscillating. Remember, when an object oscillates, it creates a wave. It gives off energy in the form of a wave, and that wave has a frequency. That energy has a frequency. I always tell students, a wave is nothing more than organized energy, and that wave has a frequency. So as that energy moves out from that oscillating system, that energy could get transferred to another object, and it will then force that object to oscillate. That forced oscillation is what we call resonance. And in particular, if we force an object to oscillate at its natural frequency, then that's what we're talking about. Those two objects are in vibrating or oscillating in resonance. Okay. That's a very useful phenomena when we talk about, for example, tuning instruments. So like if you're trying to tune a guitar, you want all the strings to, vibrate in resonance. Or tuning a piano. Resonance also can have a destructive capability. So sometimes if you cause if objects vibrate in resonance, one of those objects might be damaged because it's oscillating at its natural frequency, and because it's receiving energy, that oscillation will have, a larger amplitude, and that's dangerous, for example, for bridges. So imagine an earthquake, a seismic wave. Remember, they say that's a wave moving through the ground, but there's energy being released. And let's say some of that energy is absorbed by a bridge. And so that bridge starts to oscillate and vibrate at that frequency of the energy that is receiving from the earthquake. Well, that bridge is going to start to oscillate back and forth. And I don't know about you, but I don't want to be on any bridges that are oscillating at all. Okay. Especially not when there's an earthquake. All right. That phenomena is also destructive when you see the opera singer hit the note and shatter the glass. How does that work? Well, the opera singer releases a note that has a certain frequency, a certain amount of energy, and that energy associated with that note gets transferred to the glass. Because remember, that the frequency of that note is the frequency of oscillation for the wave that's being created. That wave is energy, and that energy gets transferred to the glass, causing those molecules in the glass to oscillate back and forth more energetically. Well, glass molecules are not supposed to move that wildly with that much energy. Remember, I told you a solid has molecules that do oscillate, but when they get too energetic, the glass will shatter. So that's what's going on. So you have cases where resonance can be beneficial. You have cases where resonance can be damaging. One other important property that we measure is wave speed. We talked about the idea of frequency already. Another property that we need to understand in order to measure wave speed is the wavelength. Wavelength is very easy to interpret. It is the length of our wave. How long is our wave? Well, how do we measure how long our wave is? We measure from one peak to the next. You can see in the picture. And we use the symbol lambda to represent the wavelength. Lambda looks like that upside down, funny looking Y. It's a Greek letter, lambda. And it is used to represent wavelength, the length of our wave. Okay. And so when we multiply frequency times wavelength, we get our wave speed. Okay. this formula that's in the box, this speed of our wave, this is what we call the universal wave equation. The universal wave equation, okay? Because all waves will have a speed formula that looks similar to this form, okay? What types of waves are there? Well, there are transverse waves, which, oh, I do apologize. My internet connection is bouncing a little bit here. So
yeah,
there,
you went out for at least probably 10 seconds.
did you catch anything of the last slide, or did it go out right here?
It from the last slide, it broke up.
Okay, so I'll do that one again. I'll do it again, just to make sure. I don't want them to miss anything here. So there are certain properties that we measure besides period, besides amplitude when dealing with our wave, okay? I mentioned to you that amplitude was the height of our wave, and you can see that depicted in the formula here, x. The minus x here just tells us that it's below our equilibrium point, okay? But it's still, the distance is x. That's the amplitude, the maximum or peak height of our wave. The other important property is the wavelength, the length of the wave, okay? And we measure the length of the wave by going from one peak to the next. We measure the distance from one peak to the next. And we use this symbol lambda, which looks like a funny upside down looking Y. It's a Greek letter, lambda, and we use it for wavelength, the length of our wave, okay? When we multiply the frequency of the wave, remember frequency is how many times per second does the wave repeat itself. Frequency, we multiply that times wavelength and we get the wave speed, okay? And this formula for wave speed is what we call the universal wave equation, because any type of wave will follow a similar format to this one when finding the speed, okay? I think I caught up on that slide. All right, so what types of waves are there, okay? So there are transverse waves, and the transverse wave has the medium being disturbed perpendicular to its direction of travel, okay? Transverse wave, all right? And light waves are typically faster than longitudinal waves, which I'll talk about in a moment, because all light waves are transverse waves, okay? Now, I know light waves don't have a medium, don't have to have a medium, but in the instance that a transverse wave is propagating through a medium, that medium is going to be disturbed perpendicular to the direction of travel for our wave, which you'll remember is what? Energy, right? A longitudinal wave, by contrast, has a disturbance parallel to its travel. So the medium is disturbed parallel to the travel of our energy, okay? And so you can see both of them in the picture. They're using a slinky to illustrate. So the first picture on the left, that's a transverse wave. So they're moving the slinky up and down, and the energy or the wave is propagating out toward forward, in a forward direction from the individual that's holding it, right? All right, so the medium vibration and the energy are perpendicular to one another. The longitudinal wave is represented by the picture on the right. And in this particular case, the vibration of our medium is back and forth. You can see here by the arrows, right, represented by the motion of the person's hand, back and forth. But the energy or the wave propagates forward in that case, right? So they are parallel to each other because they're both along the same direction. All right. So a sound wave is an example of a longitudinal wave. And that's why we typically say that longitudinal waves move slower than transverse waves, because longitudinal waves are associated with sound waves, transverse waves are associated with light waves. We won't get too deep into this idea of superposition and interference. What you need to understand from this is that we can add waves together. We can add waves together. And if we add them so that they are create a larger amplitude because they're superimposed in phase on top of one another. You could imagine two waves that are totally identical adding together so that they make a larger wave. We call that constructive interference. And then you can imagine taking two waves and adding them together so that they cancel each other out or make a smaller wave, and we call that destructive interference. Okay. So a standing wave, you could think of a wave being bound on two ends, and you have two waves being added together where they're staying within certain boundaries. So they can't really propagate, they're stuck. Okay. All right. And then nodes are those two endpoints for a standing wave where the wave can't move past those 2 points. It's stuck between those nodes. Okay. And we call an antinode is a location in our standing wave where the amplitude is, highest.
I think you should let him finish.
Somebody's mic is open. I'm not sure. Okay. All right. Intensity. So as I mentioned, waves carry energy. Okay. And that the magnitude or the size of that energy, the amount of energy is related to the amplitude. Okay. In fact, I always tell people, when you want to make your sound louder, if you want to pump up the volume, you use an amplifier, right? To have a bigger sound, more energy, more intensity. Okay. And so the intensity of a wave is measured in decibels in our metric system, decibels. All right. The way you calculate the intensity is you look at the power per unit area. So when we break down a decibel, you see that's watts for power and meters squared for area. So watts per meter squared is what we call a decibel. Okay. So intensity. All right. So that's pretty much what I wanted to cover here on waves for you. I do want to look at one other thing, but we'll take a sneak peek at that on Wednesday, because as a kind of a quick and dirty review on Wednesday, we'll take a look at the speed of sound. I'm particularly interested in that. We'll take a look at that. We'll talk about I'll answer any questions you have about the project, and we'll kind of do a quick and dirty overview of what you have left on your plate. Okay. So Wednesday, we'll look at the speed of sound, do a Q&A on the project. We'll take an overview of what we have remaining in the course, and I'll work on getting the videos from last Wednesday published for you, and you take a look at the project video between now and then. All right? Any questions? All right, I'm going to stop my share. So if you think of anything that you want to ask me between now and Wednesday, shoot me an email. Otherwise, Wednesday we'll do a good Q&A, and that'll be the last time you have to hear from me lecturing. Take care, Matthew.
Thank you.
All right, take care. Bye now.